Um, my name is Eseri Inyanga. I'm a graduate student at Jomo Kenyatta University of Agriculture and Technology. I'd like to do a video presentation on a paper I did regarding optimization of dynamic transmission network expansion planning using binary particle sum optimization algorithm. Let me share the screen. The contents of this presentation are objectives, scope, assumptions, methodologies, and the results and discussion. I'll begin. The main objective was to optimize DTNEP using binary particle sum optimization algorithm while considering the voltage constraint. These can be broken down into 4 specific objectives. Number 1, model test systems run AC load flow simulations and grow load demand and generation requirements that will be able to achieve congestion for reactive power compensation and network expansion. 2, to formulate DTNEP problem so as to be able to minimize the capital costs of new transmission lines and power losses for 10-year planning horizon. To apply improved BPSO for optimizing DTNEP results, and finally, to test the effectiveness and validate the algorithm on the Garver 6-bus system. The scope is limited to the following. Static compensators are to be used in the reactive power compensation because 1, of their fast control, 2, small physical equipment footprint, and lastly, because they are economical. Number 2, difference between dynamic and static TNEPs is that dynamic answers where, what, and when transmission facilities are to be added to the network throughout the planning period, unlike static, which answers only where and what should be added at the final planning year. The total costs are the sum of the capital costs of new transmission lines and the power losses. And the power losses considered in the total cost formulations are going to be limited to the losses from heat transfer through its lines conductors. The candidate lines are selected between 2 buses on the existing or new right-of-way, and also the cost of acquiring the new right-of-way is not included in the total cost formulation. The assumptions are 1, the demand is taken to increase by 10% annually at a constant power factor at every bus. The transmission lines were assumed to be of short and medium length to allow the study of thermal ratings of the lines and the voltage regulation effect on the transmission lines transfer capability. During load forecasting, it is assumed that new load centers can be created in the system. The methodology, 1, the testing of the model system, AC load flow simulations, and the growing of the load demand generation requirement to achieve the congestion and reactive power compensation for network expansion is as below. Table 1 gives the load data of the Garver 6-bus system, the active and reactive power of the bus loads. The table 2 gives generator data at buses 1, 3, and 6, capacities of 150, 360, 600 respectively, and active generation of 90, 120, and 545 megawatts respectively. The 6-bus system consists of 6 transmission lines and 5 load buses, and the total demand is 190 megawatts. Bus 6 over here is taken as a pre-planned bus, and the whole system is assumed to be of single voltage of 235 kilovolts. In the reactive power compensation, if the voltage in a particular bus was found to be below 0.9 pu, the reactive power was injected to that bus to improve the voltage, and this was done in increments of 10 MVR, and then the system is re-evaluated to see if the bus voltage has improved. The line loadings are monitored to be below their capacities. For example, if the bus voltage were restored to within the set limits, that is plus or minus 5%, the transmission lines were loaded below their thermal capacities. The system loads and generation requirements were increased by 10% on every load buses at a constant power factor. The various generation units were also brought online so that the supply and demand supply matched the demand. This process is repeated until the transmission lines loading limits were violated, and then the system congestion is created. The simulations were performed for base case 1, for the reactive power resource injection, case 2 and 3, where there was a 10% load growth in each case, and case 6, where a further reactive power resource injection occurred, and cases 5 and 6, where there was a further 10% load growth in each case. The second specific objective, formulation of DTNEP problem, we see that equation 1 gives the total cost, which is given by the cost of the construction of the transmission lines plus the cost of losses, where T is the number of the expansion period, at a maximum of n, which is equal to 10, and I is the candidate line from a candidate pool, LC. This is expanded further into 2 to include the discounted inflation rate given by K and equation 4 here. And the loss can be formulated by this number of hours, 878,760 hours, the cost of a unit of megawatt, a unit of energy, and K loss is the loss coefficient, multiplied by the loss at that particular expansion year. And this can be further expanded to include the load growth coefficient and the losses as given in question 6. These objective function is subject to the constraints 1 and 2, the voltage limits, which requires it to be limited to between 0.95 to 1.05 pu, as given in question 8, and the line loading limits capacities, as given in question 9. Fitness function in 10 enforces these 2 constraints with a penalty of B, which is assumed to be 10 raised to the power 6, applied to any violations of the voltage and the transmission line loadings. The scope objective 3 includes application of BPSO to optimize the results. The particle as interpreted as probability of a particle change of state 1, that being the velocity of our original BPSO, which is given by the velocity update equation given by equation 12. And it's required to be a real number in the range negative velocity max and velocity mean. This is achieved through normalization, as given in the normalization function in equation 13, that restores the velocities to between 0 and 1. And the position update equation is given as 14 and 5, which is compared to a random number R and the sigmoid value of the velocity for a true or a false position update. The disadvantage of this original BPSO is that the sigmoid function is in relation to the big values of the sigmoid function in relation to big values of negative and positive velocities. They make the algorithm not converge very well, so they tend to be stuck in the local optima. And when you're updating the position update, realize that the previous position information is not used, as seen in questions 14 and 15. So to improve this, a new probability function is proposed as given in 16. And this eliminates the drawback of the big values, positive and negative velocities. And the position update equations 17 and 18 are proposed, which decreases the probability of change. And you're able to see that the position is not good with big velocity values of changes from 0 to 1 or vice versa. This is the summary of the flowchart, which includes input of congested power transfer network data, and then you define the fitness function given in the previous slides as you initialize the IBPSO parameters according to table 1. You initialize the particle positions and velocities, then you run the power flow model, AC power flow model, evaluate the fitness function in equation 15 for each particle as you update the optical and global minimum of the particles. You check to see if the condition for convergence is met. If not, you update the particle and position velocities, particle velocity and position, and then you run this AC power flow model again. But if the condition is met, you output the transfer line solution and you end the program. Specific objective 4, test the effectiveness and validate algorithm on Garver 6 bus system. The methodology was tested on Garver 6, and the results obtained are validated by comparing to previous similar works. So the results are as below. When you're using the active power compensation, figure 4 shows that bus 4 is violated, but to improve it, upon injection, the buses at 2, 4, and 5 are improved. And case 2 and 3, there are no violations in the voltage limits. Case 4 has a violation at bus 4. When additional 10 MVR is injected into the bus 4, the voltage profile is improved, as in case 5. Case 6 has a violation at bus 2, and beyond that, the system is considered congested. The buses 1 and 3 remain unchanged because they are the generator buses. Figure 5 shows the transmission line loading. You can see that for the base case, case 1, up to case 5, the line loadings are all below the thermal loading capacities, limit of 80%. Case 6, however, has violations in lines 2, 3, and 3, 5, as shown in the graph. You can attribute that to the characteristics of a congested power system, which justifies network expansion. When we look at the active power losses, as the load demand increased, the losses are also increased. However, there's a drop in case 1 and case 5 from 1.048 to 1.005 and from 1.248 to 1.212%. This is attributed to the reactive power injection at these buses. With the drops, the network system adequacy is improved and the active power is also improved. The results for DTNEP is as below. When you simulate both BPSO and IBPSO, you get this convergence curve in figure 7. You can see that BPSO has fast convergence. The speed is good compared to the developed methodology. However, for IBPSO, the particles are able to jump out of the local optima and search in a space area of the solution space. And this gives an increased position in the algorithm. We ran the algorithm several times to select the optimal results. The expansion plan, when compared to previous works, it was linear programming and L-shade. You find that IBPSO has $190, which is lower compared to the other two, justifying the use of the developed methodology. In the two scenarios that were involved in this research, neglecting and considering voltage limits, further 6 lines were required when considering voltage limits, raising the construction cost to $288.6 million US, and a penalty of $100 for voltage violations at bus 4. The voltage profile for considering and without considering voltage limits is below. You can see that the magnitude at bus 2 and 4, they fall below the target. Near 7, bus 4 is the lowest at 0.8649 per unit. In figure 9, all the voltage magnitudes were above the target, and at bus 4 in the 7 was penalized $100 for limit violation. Transmission line loading, you look at without considering voltage limits, they all fall below 100%, and the power is also still considered operation. However, the lines 3, 5 in years 1 to 3 and 8 to 9, line 2, 3 in years 5 to 8, and line 1, 4, and 2, 6, each in the years 8 to 10 above, are above the targets. In year 8, lines 2, 3, and 3, 5 read up to nearly 99% of the thermal capacities. In figure 11, when considering voltage limits, the loading is reduced to below target, and system adequacy for power transfer is improved. The active power losses is below. There's the highest 6.05% in year 8, and the reduction is evident in these years, in year 8 and year 6, in year 8 and in year 5, which is evident through to year 10. The power loss is inversely proportional to voltage squared. So when you improve the voltage profile, you're able to reduce the line loading and lowering the power losses. Any lowering in the losses is a significant savings in the investment costs, considering that is an operational cost. In conclusion, the two scenarios, neglecting and considering voltage limits, shows that the role of the voltage limits on transmission line capability and power system transfer is to improve its power system efficiency. It also eliminates system congestion, showing a voltage stable and congested network system. The operation cost resulting from transmission losses is also lowered by up to 23.19%, and the expansion cost for voltage considerations is higher. This is attributed to the fact that you need to add more lines to be able to accommodate the system overloads for voltage stability. This methodology can be implemented on large power systems such as IE30 bus and IEEE 118 bus systems, and can also be hybridized with the IBPSO algorithm so that you're able to improve on the speed of convergence. Finally, table 4 gives the value of parameters as were used in the developed methodology. That's the end of the presentation. For any questions, please email to faithinyanga@gmail.com. Thank you.